This diagram here shows the equipotentials between two charged parallel plates. As you can see, the equipotentials are equally spaced. The spacing between the feed lines and the equipotentials actually show us indicate the strength of the field between them. And because they're equally spaced, that tells us the electric field strength between these two plates is constant. It's the same anywhere between these two plates. And that's what we expect in a uniform field like this. And if we draw the field lines, we get the same thing. They're equally spaced. Another thing you need to notice is that the angle between the field lines and the equipotentials are always 90 degrees. So wherever they meet, the field lines and the equipotentials are always 90 degrees to each other. I'm going to plot this graph of electric potential against distance from the positive plate. As I move away from the positive plate, the potential decreases from plus 20 all the way to minus 20 at a steady rate like this. Another useful equation that you should learn is electric field strength, which is measured in newtons per coulomb normally, is equal to the change in potential, which is joules per coulomb, divided by the distance over which that change in potential is occurring. And obviously for distance, we normally use meters. Now for voltage or change in potential difference, we can also use volts. Okay, so in which case you're equally justified in using volts per meter for electric field strength. Okay, so this equation tells us that the electric field strength can be determined from the potential gradient, or basically the gradient of this potential against distance graph. So let's do that. So electric field strength is equal to change in potential, so going from plus 20 to minus 20, so change is 40, divided by the distance, and I'm going to make sure the distance over which I'm taking that gradient there is in meters as well. So I'm going to divide 4 centimeters by 100 to give me an electric field strength of 1000 volts per meter. And now I can use this to plot an electric field strength against distance graph. You can see the gradient is the same across. That means the electric field strength is the same from the positive plate to the negative plate. It's constant and there's a constant value of 1000 volts per meter. From the bottom graph of electric field strength against distance, there's some meaningful information we can get. Because electric field strength times change in distance is going to equal change in potential, the area under the electric field strength against distance graph is equal to electric potential, change in electric potential. So let's say we have a charge going from A to B, okay, going from the 1 centimeter mark to the 3 centimeter mark. So we can determine the change in potential without using the top graph or reading from the diagram. We can determine it by figuring out the area from across which it's moved. Okay, so in this case, this area here is shaded from 1 centimeter to 3 centimeters. So that's going to be the change in potential. So we can get that by doing 1000 times 0.02. That's the 2 centimeters turned into meters there. And that gives us change in potential of minus 20 joules per coulomb. Now the potential energy is decreasing because the positive charge would be attracted towards the negative plate. So it actually lose electric potential energy. Now we have a radial field with the equipotentials drawn around it. Once again, the closeness of the field lines and the equipotentials show the strength of the field. And as you can see, closer you are to the charge, the closer the equipotentials are to each other, the closer the field lines are to each other. Also, the field lines and the equipotential are always 90 degrees to each other again. So if you look at different points on the diagram here, at every point where the field lines and the equipotentials meet, it's always 90 degrees to each other. Okay, I'm going to plot an electric potential against distance graph. So using this equation, we know it's going to be an inverse relationship between electric potential and distance from the center. So it's going to look a bit like this. Okay, and the equation that we just learned a minute ago tells us the gradient of this potential against distance graph is the electric field strength. So I'm going to use that to complete this graph here. I'm going to see how the electric field strength changes. So I'm going to take a gradient over here, and if I use the tangent there at that point, I can figure out the electric field strength. So I'm going to skip that step. So it's roughly 150 kilovolts per meter. Okay, so I'm going to plot that point. I'm going to repeat this step, and as you can see, the gradient is decreasing as we move towards right, and that's what we expect. As we move further away from the charge, the electric field strength would decrease. So we get a curve that looks a bit like this. And as you can see, this is the electric field strength around the radial in the radial field. So it follows this pattern here, which comes from Coulomb's law. Okay, let's say we have a charged particle moving from A to B, and the only graph that we have is the bottom graph here, electric field strength against distance. Using this equation, electric field strength times change in distance is equal to change in potential, we can figure out the energy required to go from A to B, or the energy released, the change in electric potential energy. That comes from the area under this graph. So let's say it's moving from 5 centimeters to 10 centimeters. So you'd mark those points off and you'd figure out the area maybe by chopping up into trapeziums or counting the squares. And this area here was going to equal the change in potential. To figure out the change in electric potential energy, you simply have to multiply by the charge that you're moving. So if it's an electron, you do it by 1.6 times 10⁻⁻19, and that would give you the change in potential energy.